Okay, welcome to this section on Introduction to Artificial Intelligence. We'll introduce AI here, talk about some of its use cases, as well as overviewing the pre-work. What we learned today is a broad understanding of what AI is and some of their applications. We'll start with the definition of AI. What is AI? Then we'll distinguish AI from neural networks, which is a specific type of AI. We'll also talk about two main subcomponents of AI, which is natural language processing, or NLP, that deals with text, audio, speech, or anything that's related to language. We'll also talk about computer vision, which deals with images, videos, anything that is in visual format. So what is AI? AI by definition is intelligence demonstrated by machines, just like intelligence demonstrated by human beings or animals. This intelligence should be goal-oriented, and at the same time, this decision should be rational. So in case of a cat that is thirsty and is looking for water, the cat starts searching for water, and when the cat finds the water, it starts drinking it. So it's goal-oriented, and throughout the whole process, the cat is acting rationally. For AI or for a computer, this rational act is nothing new. If you have played chess on a computer before, you can see that starting from 2-3 decades ago, computers were intelligent enough to compete with humans. Traditional AI use what we call expert systems. And for expert systems, you have to specifically tell the computer what step to take at each step of the process. So before your AI model is developed, you have to think about all the possible outcomes and different variations that can happen, and tell the machine in an if-then type state what actions to take, what actions to avoid. So you had to program the machine. Well, this was done many decades ago and still pretty much done in many areas to this day. But what's become really fascinating about AI is a subfield called machine learning. And what machine learning does is, instead of asking the designer of the program to tell it what to do at each step, it looks at the data and tries to come up with its own set of steps and mathematical formula based on the data that it's seen, and it automatically generates and creates and constructs what steps to take. Let's take the task of image classification, for example. We have an image, which is an image of a cat here, as opposed to dogs and other animals. And we want to use the traditional expert systems method to classify or identify this as a cat. Well, first we have to tell the machine, please look at the image and find out if the face is round, let's say, or does it have ears, and are the ears pointy? And does it have fur? If all of these is true, it is a cat. If one of these is not true, then it's not a cat. This is the expert systems way. Well, it has some shortcomings. Let's say a given image of a dog checks all these boxes. It has ears, it is furry, it has round head, but it's not a cat. So for expert systems, if you don't think about all the possibilities, all the different variations of your task, it has high potential to fail. Now let's try to solve this with machine learning. You give the model a lot of images of a cat, different images for different breeds, and at the same time give it images of dogs, human beings, different animals and species. Then the model will look at the image, and it will also look at the label that you give it. You say, okay, this image is a cat, the other image, it's a dog. And the model automatically will try to understand what certain nuanced features and characteristics a cat has, as opposed to a dog or a human. And without explicitly programming the model how to identify a cat, it can identify a cat. And surprisingly, the accuracy using machine learning is much superior to the traditional expert systems. Even though modern artificial intelligence has shown promising results, it's been sort of limited to different subcategories. So we have one field which is called computer vision that mostly deals with visual data. We have another field called NLP, which mostly deals with language data. And we hardly see an intersection between these two subfields. Although some research has been done on combining, let's say, images with text, as you see in this image. This is called image captioning in deep learning. You give it an image and the machine tries to explain what is happening in the image. Man in black shirt is playing the guitar. Or for this image, construction worker in orange, safety vest is working on road. So there are some interdisciplinary applications of AI, but the ultimate goal for some AI researchers is to derive at a sort of general artificial intelligence, which, just like a human being, can take inputs from different sources: visual, audio, olfactory, many different sources, combine them together and act and behave accordingly. But in reality, this is a long-term dream which has not materialized yet. So at this point, most AI applications are specific to one of these domains: computer vision, natural language processing, reinforcement learning, which we'll discuss later. There are different namings for different artificial intelligence methods. We hear them a lot in our everyday life. We hear deep learning, we hear machine learning, we hear AI itself, we hear neural networks. So how can we really distinguish the nuances and differences between these names? AI is the umbrella term. As I said before, if a machine shows intelligence of any form, we say it possesses AI. Then we have a subcategory of AI, which is called machine learning. And as we said before, machine learning is an AI method that learns patterns of data from the data itself without being explicitly told what to look for, what to do. Then there's a subcategory of machine learning called neural networks, which we'll discuss later, and it is inspired by the human brain. It has a series of neurons that are connected to each other, and they take the input, they produce an output. Now, if a neural network is deep enough, meaning it has enough layers in it, we call that a deep neural network or deep learning. And most of the success stories of AI that we hear on the news, social media, are actually deep learning methods applied to data. Then we also have different subcategories of artificial intelligence, natural language processing, and computer vision, which we'll discuss later. We also have four main ways for machines to learn. So broadly speaking, we have supervised learning, unsupervised learning, reinforcement learning, and semi-supervised learning. Let's start with supervised learning. This is arguably one of the most common ways of training a machine learning model. For supervised learning, if we have a task, let's say we want to classify our emails into spam and not spam, this is what's done on your email service if you have Gmail or Yahoo or different email service providers. This is mostly done automatically for you. Now, if we want to build such a machine that can filter spam from important emails, we can use a supervised learning approach. For supervised learning, we need inputs and labels. And what the machine will do, of course, in this example, inputs are actual emails that we have historically collected, and labels would be the tag that it is a spam or it's not a spam, which we have possibly manually labeled. We've read each email and labeled them spam. The next email, not spam. So for supervised learning, the model will take in the input, which is the text of the emails, and look at the output. Let's say this one is a spam. Then it will learn, okay, this is how a spam email looks like. Then it'll look at another example, which is not a spam. It'll read the text, look at the label and say, okay, this is how a not spam email looks like. And if you give it enough data, it will eventually be able to find patterns in the text of spam versus non-spam emails and be able to, with high accuracy, classify spam and not spam. So this is how supervised learning works. And this is arguably, again, one of the most common ways to train a neural network or a machine learning model. Another method is unsupervised learning. For unsupervised learning, we don't have any specific labels for our input data. We just have raw input data and we want to do some analysis on it. Maybe we want to find some patterns in the data. Maybe we want to cluster the data based on the distribution of the data, based on the distances of each data points. So if we take the example of emails, we have 10,000 different emails, none of them have labels. We can use unsupervised learning to find email texts that are similar to each other. Of course, at the end, we will not necessarily be able to cluster the emails into spam and not spam, but the model can have a look at the distribution. Can find some patterns in the email text and say, okay, these 5,000 sets of emails are pretty similar. The other 10,000 emails are pretty similar. So it can create clusters of emails. And unsupervised learning is a good and useful tool for exploratory data analysis. When you just receive the data and you want to gain some insight about the distribution of different data points, unsupervised learning could be very helpful. The next example, or the next type of neural networks and how we can train them, is called reinforcement learning. Reinforcement learning is based on a state, which means the state of the world or the environment that we live in. It also has an agent, which is the machine learning model. And this agent, which is the model, in this example, it is an arm robot, is trying to interact and perform and live within this environment in an efficient way, in an intelligent way. And as we said, by intelligent, we mean in a rational way to achieve a certain task. So these armed robots, their purpose is to pick up items from one tray and put it into another tray. So this is their task. So if they act rationally and take steps that are rational and oriented towards the goal, they will pick up the object and put it into the tray. So to train an AI model using reinforcement learning, we have to give them rewards. And rewards determine and tell the model when it is performing well, when it's doing a good job, or when it's not performing well. So if the robot just stays there and doesn't do anything, well, we could give it negative reward and kind of entice it to act. If it acts, picks up the objects and drops it instantly, we can also give it negative reward. Maybe a smaller negative reward, but negative nonetheless. So this process is really repetitive. The robot will start really poorly because it doesn't know how to interact in the environment, and it might pick up the object, drop it, might not know how to move the arms and fingers. But as we train it hundreds of thousands, maybe even millions of times, it'll eventually learn how to perform the task that we give it to. And the applications of reinforcement learning are very broad. One of the most notable examples is robotics, how to train robots to navigate into real-life environments. Another is autonomous driving. How can we train a car to drive on an actual road without hitting the curb, going to the sidewalk, hitting pedestrians, hitting other cars? And this is a very active area of research and practice. The final way of training neural networks is semi-supervised learning. Now, semi-supervised learning combines the ideas from supervised learning and unsupervised learning. Why is semi-supervised learning interesting? First, we have much more unlabeled data than labeled data. Let's say we are working with documents. Just Amazon and Google's book data sets and databases have hundreds of thousands or even millions of books. Now, let's say our task is to do OCR, recognize the characters from scanned books and turn them into searchable text. Well, gathering data and for this task is kind of a tedious task. It's kind of expensive too. It's really hard to take 1 million different books, which each of which has 200 to 1,000 pages, and ask a human being, of course, to read them and type in each word. So collecting data for this task is pretty expensive, pretty time consuming. So what we can do is to use semi-supervised learning. So by definition, the way semi-supervised learning works is that it takes some labeled data, maybe limited number of labeled data, let's say 1,000, and a lot of unlabeled data, maybe 1 million, and tries to get some understanding of how the distribution of the input is using the unlabeled data, and eventually using the limited labeled data that we have, be able to perform the specific task that we want. So using unlabeled data to get insight and knowledge about the structure of the data, and then use the limited label data to perform the actual task. In the case of classifying different objects, of course, we have a lot of images on the internet that do not have labels. So we can scrape them off the internet. We'll end up having 10, 20 million different images. Then we can have potentially 1,000, 2,000 labeled images. Feed them all to a neural network. The neural network will learn the underlying structure of each image, different distributions of the image, and then use the 1,000 or 2,000 labeled images to be able to label the whole data set or the whole database with high accuracy, of course. Semi-supervised learning is helpful for many tasks in many domains. For instance, in medical practices, obtaining labeled data means asking medical doctors or specialists to label your data, which is a very expensive and time-consuming task. I also mentioned the example of documents. Semi-supervised learning is an active area of research, and a lot of papers are published every year on different new algorithms, how to improve existing algorithms, how to improve the accuracy and the speed. So let's talk about neural networks now. As I said before, neural networks are a subset of machine learning model. The most famous type of neural network is a deep neural network, which we also call deep learning, and they are really good at finding nonlinear patterns. This is a simple illustration of what a neural network is. So we have some inputs, we have some intermediary or hidden layers, and we have some outputs. So our input data is input here into the model, goes through several hidden layers. Some mathematical operations are performed on them, and eventually an output is produced. So in the example of image classification, our input data would be an image. We turn the image into numeric format, so we turn the pixel values into floating point numbers that a machine can understand and do mathematical operations on. Then our image goes through the neural network, through different hidden layers. Then the mathematical operation is performed on the input data and some output is produced. Then we take the final output, which is also called our predicted output, and we compare that with the actual ground truth label, the one that we humans label for the input image. From this comparison, a loss function is used to create a loss, and a loss is just how close your prediction to the actual label is. So if the model is predicting something that is very close to the label, the loss will be low. If it's far off from the label, the loss will be high. Then we can use a very smart and interesting mathematical operation, which is called gradient descent, to decrease this loss that we got here. The way it works is first we perform back propagation. So we go from the loss all the way back to the first step and calculate the gradient of the loss with respect to every parameter or number in the neural network. This is called back propagation. So the gradient here says, or tells us, if we change the parameter of each parameter of the neural network, how much does it affect the value of our loss? Therefore, if we adjust the value of the parameters based on the gradients that we just calculated, we can actually decrease the loss and train the model. So this is how neural networks are trained, by using gradient descent. That's an algorithm. Really, what distinguishes neural networks from traditional statistical methods, it's its ability to identify nonlinear patterns. So let's say we know about regressions, specifically linear regression, and we wish to find a line that passes really well through our data. So this first example, we have the y-axis here and the x-axis there. So y, x. This seemed like a pretty linear function. So if this is our y, x is probably equal to y. So y equals x. So we can use simple linear regression to find a line that passes through this. If our function is not linear but it is quadratic, so this is our y, this is our x, well, we cannot really pass a line through this. What we can do is to pass a quadratic function, something in the form of y equals ax squared plus bx plus c. So although it is nonlinear, but we can find some simple function to model this data. But if our data looks something like this example right here, let me put it somewhere we can read it. If the data looks something like this, scattered data without any noticeable patterns, and it's really hard to pass a line or even a curve into this, a neural network would be powerful enough to find a way to illustrate or to capture this. So one way could be to think outside the box, to draw a circle around the data. But the power of neural networks is not that it can only just find different nonlinear or linear patterns, is the fact that it automatically, without us specifically telling it what function to use, it will find out the right function. So no matter which one of these curves or scatter plots you give a neural network, it will automatically find the underlying function. So yeah, for us humans, it's easy to say, okay, y equals x. And for this one, we have to know some mathematical knowledge to say y is a quadratic function. Here we have to know how a circle function looks like. So we have to work with the radial coordinate system. But the neural network is agnostic to any of this. It just looks at the data, does some mathematical operations, and finds the underlying function. So this is what distinguishes deep neural networks from simpler statistical models like linear regression. Now let's discuss some of the similarities of neural networks and human brain. Because historically, neural networks were inspired from the nervous system and the brain of human beings. That's why a lot of the jargon that I use today, like neurons and hidden layers, these were kind of similar to the neuroscientific words for the human brain and the cortex. So this is what a typical neuron in the body looks like. It has dendrites, which are input parts of the neuron. So it receives, loosely speaking, it receives data, or let's say input signals, through dendrites. Then the data or the signal travels through the dendrite, goes into the cell's body, which is called soma, and it has a nucleus, the different components that can process the data, just like a machine learning model, a deep learning model does. So it goes through, gets processed, and the signal kind of converges here at this hill. We call it axon hillock. So the data or the processed data is gathered here. Then it travels through the axon all the way to different endpoints in the axon, which are called terminal buttons. And this process is like a chain. So the output of this whole neuron would become, so this output of this whole neuron will become input into another neuron with its own set of dendrites. And this process continues. The output of this next neuron goes to another neuron, and so on and so forth. And at each step, starting with raw data, let's say our occipital part of the brain, which is at the back of the head, light rays go through the eye to the retina and through some neurons into the occipital part of the brain. So raw light rays, which are the raw signals, go through different dendrites, get processed, and go to the next neuron. At each step, the raw data gets processed and becomes more abstract. So if we are looking at an image of, or we are looking at a building, the first few layers process the input raw rays into maybe some lines, some vertical lines, maybe some basic colors. Then the next neuron takes all these basic abstractions, these lines, these simple colors, and puts them together to create more complex shapes. Okay, it's a rectangle, it's a 3D rectangle. Then it goes to next and next and next neurons, and these basic shapes eventually become something like a building, a complex abstraction that the brain creates. And then we say, okay, oh, I'm seeing a building. And this is, interestingly, how deep neural networks also function. When you feed them an image of a building, they create simple abstractions and go from these simple abstractions to more complex ones. So this is a side-by-side display of an actual human neuron and a neuron in a neural network, artificial neural network. So let's call it artificial neuron and the actual neuron. So these analogies are kind of interesting because here in the nucleus, we said we have a bunch of mathematical operations in the brain. The same is true for the neuron of a neural network. The inputs, we said, these are signals from different senses. Maybe this audio, maybe it's image signals. The same is true for an artificial neuron. So V1, V2, Vn minus 1, Vn. These are different inputs. W1, W2, all the way to Wn are the parameters of a neuron. And what happens is the input is multiplied by the parameters. We do a matrix multiplication to calculate the output. So in neural networks, the actual mathematical operations to process the raw signal and turn it into more abstract data to be fed to the next layer is actually this simple mathematical operation. So you take your inputs, multiply it by your parameters, and you'll have your outputs. There's another step that we have to do to make neural networks function. Because mathematically, if you take some input I, then multiply it by some parameters W1, then we take the output of this as the input to the next layer and multiply it by the parameters of the next layer and do it indefinitely, let's say for n times. What we'll end up with is just a linear combination of this whole operation. So we can represent this whole thing as I multiplied by a WX, let's say. So practically you might say there's no use in multiplying different matrices and vectors, because if you multiply them, you can just combine all the W's here into WX, and that's just one multiplication. So there would be no point of having different neurons in a neural network unless we have some nonlinearity. So what is nonlinearity? Nonlinearity is a function that is not linear. So you could think of infinite number of functions that are not linear. One of the most famous ones that's used in neural networks is a ReLU function, which has a very simple shape and very easy and inexpensive to calculate. It says for any negative number, let's say this is our x, set the value to 0. For any positive number, set the value as it is. So that would be x. This is a nonlinear function and one of the most widely used nonlinear functions in neural networks. So how does this nonlinearity help us in learning complex patterns? There's a theory in mathematics which is called the universal approximation theorem. So what this theorem says is that if we have a series of functions, just like this one, a simple mathematical multiplication, followed by non-linearities or nonlinear functions, which again is followed by another matrix multiplication, and again followed by nonlinearities. If this chain of multiplications and nonlinearities, are long enough, or using deep learning jargon, they are deep enough, we theoretically can approximate any function with any level of accuracy or proximity as we want. So this is a very strong theorem. So what it means, if we make our neural network deep enough and we put nonlinearities after each multiplication, we can pretty much model any function. Of course, it does not mean that neural networks magically can solve any task without any limitations. Of course, there are some practical limitations, although not theoretical, but practical limitations. So one of the main limitations that neural networks have is that neural networks are really data hungry. It means if we have just 10 examples, we'll probably not be able to train a neural network from scratch. Most of these state-of-the-art machine learning and deep learning algorithms are trained on huge amounts of data. So we have ImageNet, which has more than 1 million images to classify 1,000 categories of objects. Superhuman accuracy on ImageNet these days, thanks to deep, complex neural network architectures, but also because the ImageNet size is really large. For NLP, for example, we also have Wikitext 103, which has like billions of words in it. So that's one requirement for neural networks. We need large amounts of data, and we need deep neural networks. So one implication that this has is that if we have a lot of data and the mathematical operations that we're performing on the data are really complex, then we will need a lot of computation power. And it will take a long amount of time for the model to be trained. So that's one thing we have to take into consideration. One simple rule of thumb is neural networks can vary in depth. So we can have one hidden layer, we can have two hidden layers, so on. As a rule of thumb, if a neural network has 2 layers or more, it's considered a deep neural network. So if you're working with 2 layers or more, you can say, I'm working with deep learning. But neural networks not only can vary in their depth, they also can vary in their width. So the number of neurons in each layer can also vary. This is a hyperparameter that we can tune and change. So a lot of state-of-the-art models have, let's say, 5 or 6 small number of neurons in each layer. Some of them have hundreds of neurons in each layer. Each one of these have their own advantages and disadvantages, of course. So one example would be if your network is really wide, we will need a lot more computation than compared to when it is relatively narrow. But if it is wider, it has more capacity, so potentially and theoretically it can explain more complex patterns. So there's always trade-offs. Natural language processing. Well, the goal of NLP is to make machines perform almost as good at human language as humans are. But language is a really complex phenomenon. You cannot say language is reading or language is thinking. It's composed of different subtasks that NLP researchers try to solve. So there's research on making machines classify different pieces of text. So let's say I have a data set that has different text in it. Then I can train an AI deep learning model that can classify the text as positive versus negative. This is called sentiment analysis. And this whole task is text classification. We can also take a long piece of text, use a deep learning model that knows how to summarize text, and create a shorter piece of text, a summary. So this is a long document and this is a summary. This is another application of NLP. Some neural networks can be trained to generate realistically sounding pieces of text. This is called language modeling. Language modeling. A language model in pop culture is really famous for generating Harry Potter sounding pieces of stories. So they've been trained on Harry Potter books, so they can generate artificial but kind of realistically sounding Harry Potter stories. We also have question answering, so you can train a model to learn how to answer questions. So if you give it a question and a piece of context, it can, with high accuracy, answer your question. This whole field of NLP is studied in the field of computational linguistics. So using machine learning for NLP is really attractive these days because, as I said earlier, in the field of NLP, let's say in books and the databases that we have for books, we have a lot of unstructured data for machine learning models to use. So if you're able to solve a task using machine learning for NLP, you can label data, you can answer questions for a large amount of unstructured and unlabeled data. Natural language processing is the study of human language. It's been traditionally studied as a subfield of computational linguistics. And the goal is to make AI understand human language and help us in many language tasks that we have, such as language classification, language generation, sentence completion, and so on. It's a very attractive subdomain of AI, specifically for this day and age where text is generated in an unprecedented amount. Take Twitter, for example. Every year, billions of tweets are produced by humans, and to study them and even analyze them and monitor them, it's very difficult if you want to do it by hand, manually, with people. So if we're able to train machine learning models to read text and analyze it and give us feedback, this could be a very powerful tool. An example would be a professional who's working in the retail industry, working for a brand, and their brand has a Twitter page, has a Facebook page, has a YouTube channel, and there are a lot of tweets and posts and comments generated for the brand. So if you can create an AI model that can look at all the text, analyze it, and give you feedback about the market sentiment, about the new products that could be in demand and we are not aware of that, about the problems about the brand image, and so on and so forth, we can gain invaluable insight from NLP. Some of the use cases of NLP are Google's products. So when you type in Google and you try to search for something, it has an autocomplete feature. As soon as you start typing, it suggests different keywords, different inputs that can be useful to you. The backbone of autocomplete feature not just on Google or other search engine platforms, but also on your smartphone's keyboard, is NLP enabled AI systems. It makes life a lot easier to have this autocomplete feature, and it saves you a lot of time, maybe gives you some suggestions for words that you're not sure about. So it's a pretty useful application. And you can take this concept and apply it to your own specific business needs and practices. Another use case is Microsoft Word's spell checking and grammar checking, also Google Docs' spell checking and grammar checking. They use NLP to understand language and notice when you're making not just a typo, but also when your sentence is not really clear or there are some grammatical errors in it. There are software that's created specifically for that. So Grammarly is one example, which is broadly used to help human beings in better communicating with each other and conveying their ideas. NLP is also applied to news feeds. So if you get your news from Google News, Apple News, Facebook, most of the time you can see that they are tailored to you. And this happens with NLP, and the algorithm takes the news, reads it, and tries to understand what the content of the news is. And then it looks at your own preferences and tries to match you with the piece of information, piece of news that you will find attractive. Another use of NLP is chatbots and voice assistants. Probably you've worked with Siri, Alexa, Google, which are personal assistants. You can talk to them, you can ask them different things about facts, you can give them orders to like set an alarm or call someone. So they use NLP to first interpret what you are saying. So they turn your voice into textual information and then analyze that text to understand your needs, your requests. And they have a huge database or knowledge base, which they can use as a source to give you information or perform tasks for you. Finally, there are translation systems like Google Translate that can with high accuracy translate from one language to another. Of course, these translation systems have been trained on gigantic corpuses of data. Let's say French to English. We have a giant corpus of French news and its corresponding English news. So they've been trained to translate the French version into English version and vice versa. So they've become really strong and powerful in translating. We can also do sentiment analysis with text. If your product in the market receives reviews, you can train an NLP model to look at those reviews and tell you what the sentiment is. Is the review positive? Is it negative? Is it neutral? Or for tweets, you can do sentiment analysis on that too, just to see what the tweet is saying is positive or is it negative. Another example is chatbots, which a lot of corporations use for their customer service. Chatbots these days can interact with users in a very natural and human-like way. And because they have access to companies' policy, service offerings, products, and all the descriptions and the details, they can pretty much solve many of the tasks that required humans previously and make it really fast and efficient to solve your customers' problems. Computer vision is another subfield of AI that, as we said before, it deals with visual image. So it could be digital images, videos, or other types of visual inputs. The application of computer vision using AI has in many tasks surpassed human level. So for instance, in image classification, state-of-the-art machine learning models outperform even humans. And by outperforming it, we mean human being classifying images gets, let's say, 94% accuracy, but the computer vision model that is trained can get 95%. That's why we call it superhuman accuracy. Recently, Google's CT scan AI machine outperforms radiologists in classifying and identifying lung cancer based on chest CT scans. These results have significant implications for the industry and for practice of machine learning, and there's a huge opportunity for everyone to take advantage of that. Computer vision tasks are relatively classified into 6 or 7 subdomains. The most basic task that computers can do really well is image classification. Just you give them an image and it will tell you what class it is. This is the cat example that I mentioned earlier. This is a cat, a dog, a human. Another task is object detection and localization. So as you can see in this image, the model creates bounding boxes around different entities and recognizes the entity. So a bounding box around a human with the label human. This is called object detection. Segmentation is also similar, but in segmentation you actually draw masks that give you precise outlines of every entity in the image. So in the example in the image, car has a bounding box that says it is a car, so this is the object detection part, but it also has a mask, kind of pinkish mask on it with the boundaries carefully and precisely drawn. This is called segmentation, and it is used in an array of domains, most importantly prominently in autonomous driving and self-driving cars. Because if you want to have a self-driving car, you need to know what objects the model should be able to see. Okay, there's a car in front of me and this is the outline of the car. There are several pedestrians on the sidewalk, there are several cyclists, and this is exactly where they are. So this is invaluable for autonomous driving. Generative modeling has become really popular these days, and the idea is if you train a model on a set of images, it can generate realistically looking images that are not in the training data. So we have many websites such as "this person does not exist." And if you go to it, it'll automatically generate a really realistically looking image of a person in really high resolution. I believe this is full HD image. And this person does not exist. The model is trained on a huge data set of human faces. Then it's able to generate new faces of people who do not exist. Video analysis is just an extension of image analysis. If we are able to process a single image for any of these tasks, to classify, to detect and localize or segment, we can do the same thing for videos, because at the end of the day, what videos are is just a bunch of frames of images put together in a series. So you can do object detection for video in real time, and it will draw bounding boxes in real time. There are several software and applications that you can download and install on your phone, and it'll use your phone's camera to look at different objects, and in real time it'll draw bounding boxes. Say, okay, this is a coffee mug, this is a dog. So how computer vision works is using a very specific type of neural network layers, which is called convolution layers. Convolution layers could be used for time series and other applications as well, but they give really high accuracy and impressive performance for images. So this task is an image classification task. The input is an image of a cat. It goes through a series of convolution layers, of course, followed by nonlinearities. So each one of these layers is followed by a nonlinearity, then goes to another convolution layer with another nonlinearity to create the fundamental neural network. And finally, it makes predictions on what class this input image could be. Here, it seems like we have 6 classes total, and the model is predicting probabilities of this image being in each class. Of course, the probabilities should sum to 1, so if we add 0.8, 0.1, and the rest, the result should be 1, because they are probabilities. And at the same time, we can look at probabilities as models' confidence about this image belonging to each class. So it says for cat, there's 0.8 or 80% probability that it's a cat. 10% probability is a dog, 2% is a rhino, hippo, elephant, and 4% is a mouse. Then we can ask the model, please give me the name of the class that has the highest probability. So it'll tell you that this image is a cat. Another use case of computer vision is facial recognition, which these days is used really broadly, not just on a surveillance type task, but in many corporations, they use facial recognition to do the security tasks for them automatically. So imagine your company uses facial recognition to let people inside the corporate's building. So if you are an employee of the company, there's a CCTV camera, looks at your face, and if it identifies you as an employee, you'll gain access into the building. There are several steps involved in facial recognition. So a CCTV camera will have a broad view of the entry door, and probably you're located right here. And it's probably looking up at you. So the first step it has to do is to crop your face to get a closer view. So this is the first step. Then your face goes through a neural network, possibly composed of different convolution layers. And some features are extracted from your image. Let's say this vector is the set of features about your face on the CCTV camera. Now, the neural network also has been trained on a set of images of you. Let's say this is you, person A. It already has been trained on tens, hundreds of images of you before. It's also been trained on a set of images of your colleagues, person B, person C. And it also has the features extracted for each one of these images. for you, for your colleague B, for your colleague C. So what it does, after cropping the image and extracting the features, it'll compare these features with the features of you and all your colleagues, all the employees in the company. Then it tries to find the closest person that matches this feature. It uses some distance metric to find which one is closest to this person right here. Identifies that, okay, this person is closest to person A. It will say, this guy right here is person A. So this is how facial recognition works. But what if a person D comes in and D is not an employee of the company? Well, it'll look at all the images and says, well, given this threshold that I already have, it's not close enough to any of the employees that I know. The distance between person D and A, B, C is really too large. So I don't recognize this person. Please call the security to come and find out what is going on. Another use case of computer vision is traffic analysis. Well, especially in bigger cities, when you cannot have police officers at every highway, intersection, traffic light, well, it's really useful to have cameras equipped with artificial intelligence to look for different things. So if a car is speeding, well, it can measure the speed. If it passes the speed limit, it can take a picture of the plate, and it can read the plate using computer vision methods to find out what the text of the plate is, and, well, send a ticket to the owner of the vehicle. If a vehicle is driving dangerously, like cutting lanes and drag racing, it can identify irregular, anomalous movements of the car. So it really helps, especially in bigger cities, to have these cameras equipped with computer vision AI to kind of reduce the workload of police officers. In summary, in this section, we learned about AI and various subdomains of AI, specifically NLP and computer vision. We looked at the different terminologies that's used: AI, neural networks, machine learning, deep learning, and we found the differences between each terminology. Then we looked at the biology of human being and what kind of comparisons we can make between a human neuron or nervous system and an artificial neuron or artificial neural network. We looked at the underpinning. We looked at the underlying process of NLP, as well as some of the applications. We also looked at computer vision, how it works with convolutional neural networks, and also different examples. Thank you so much.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.